So next speaker is Charles Hoover. Chuck is part of a color dynasty. He's the fourth generation of a family born and raised in the color world. He has plenty of experience because he was in the Hoover Color Company since 1982. The Hoover Company is now in the hands of Cathay Industries. And I think that Chuck will entertain us with a presentation on iron oxide processing and the impact on the resulting color in plastics. Always great to hear people with plenty of experience. Over to you, Chuck.
Unmute. I guess you can hear me now. Hello, my name is Charles Hoover, although most people call me Chuck. As you know, I'm a fourth generation member of a color family. I remember my first job in the color business was when I was 5 or 6, collecting pigments or collecting pebbles for pebble mills at the company. And so I've had a lifetime of pigments, and would like to share some of my unique insights in pigments and the colors that are involved there. Again, can I get some feedback? I see my presentation, but I'm not sure anybody else can.
Hey, Chuck, a question. Can you make sure to activate your camera, please?
Okay, hold on a second. Well,
bottom left of your screen.
Okay. Does that?
Okay, we're in business. Better? Thanks.
Okay, now we're going to share screen. And okay, this looks better. Sorry, Tom. Okay. Again, today my presentation is to talk to you more about iron oxide pigments and what we do as manufacturers in iron oxide pigments and what those impacts affect in plastic processing. In my mind, color is the first quality parameter where you can make the strongest, most durable, and most economical plastic. But if the color isn't right, your customers will assume that something else is wrong too. You've all heard the expression, you can only make a first impression once, and color is a large part of that first impression. Typically, I do this type of presentation live, and I like to get a certain amount of dialogue between the people listening. Obviously, we can't do that today, but I'd still like to show this slide as a conversation starter. Here we have 7 bananas, different colors, and it's surprising the preferences that people have on what banana would you eat. We're not doing any quality testing here. We're not measuring sugar levels. We're not measuring, firmness of the banana. We're strictly able to correlate all those parameters based on the appearance or the color of the banana. What's really interesting after giving these types of presentations for a while is the preference that people have for, their bananas. And the people who eat banana number 3 really have a hard time with the people who eat banana number 7. Another interesting fact is when you change the question to what banana would you buy, people actually move their color preference over too. And again, there are no QC tests here. We're strictly looking at the appearance of, that banana. So if you're in the market for a BMW, even when the performance is exactly the same, the color matters. You know, you're going to have to get me a big discount to drive that purple BMW. I know this is a review for some of you, but humor me here. You know, when we talk about color, we've heard the expression, if a tree falls in the forest and nothing is there to hear it, does it make a sound? Color is kind of similar. If nothing sees a rainbow, is it really there? There are three things we need to produce a color: a light source, a surface, and an observer. First, you need a light source, and not all light is the same. If you look at this illustration and compare the light box on the left and the light box on the right, you can see that noon daylight has a much bluer component than daylight at dusk. And that in turn affects the colors that we see. For example, you know, we know that these clouds are not orange and red, but the light of the sunset has a much redder component than daylight or the noon blue daylight, and therefore, you know, we're getting these red colors. I thought, you know, after I was done with this presentation, an interesting observation would be to take a, you know, picture of something like a Ferrari, a red Ferrari, and filter out all the red wavelengths of light. What color do you think it would be? In my mind, you're probably talking about a dull gray. Next, we need an object to interact with the light. And this is where we all come in. We as pigment suppliers supply you a powder primarily that reflects certain wavelengths of light, and you incorporate it into a, you know, resin system and mold it into a usable part. And finally, we need an observer to see that color. If there isn't an observer, you know, those wavelengths of reflected light off the pigment just fly into space until they are, you know, dissipate or absorbed by another object. One of the things that you learn in color measurements, though, that I wanted to add here is that your color sensitivity does decrease with age, and especially with the B value. So for you young color chemists, you know, working with old people like me, and we can't quite see the difference in those yellows and blues, that's why. During this presentation, I'll actually repeat myself a couple of times on important points to reinforce them. You know, when we use pigments to impart colors, but what really is the difference? You know, Mark before was talking about complex inorganic pigments. I'm talking primarily on iron oxide pigments. But really, if you look at pigments as a total group, you know, you can differentiate those by their chemistry, their particle size and shape, and their level of agglomeration or clustering. Chemistry is the, you know, the first step there. And again, if I'm repeating some of the things you heard from Mark also, I'm just taking it to a little different way. The chemistry defines the color group, not the color shade, and also the durability of that pigment. So from the chemistry, you get your light fastness, your heat stability, and your chemical resistance. You know, for example, I can look at this atomic structure of Fe2O3, and I can tell you it's a red iron oxide, but I can't tell you whether that's a light shade red iron oxide or a dark shade red iron oxide. And just as an aside, a lot of us use color index numbers. Color index numbers reflect these chemical properties, not exactly the color shade. What does define the color shade is the individual crystal size and shape. So we get both our color shade and our undertone of those colors, but also the transparency and opacity of those pigments based on the particle size and shape. And here are some examples. Both of these red iron oxides are chemically identical. You know, if you're not familiar with the way that pigment people look at pigments, the top set of chips, the darker set of chips are the pigments in a clear resin, and the bottom set are the pigments in combination with titanium dioxide to see an undertone. And so even though these two pigments are chemically identical, they differ in particle size, not shape, since they're both red iron oxides, but you get this dramatic color difference. The same thing is true with transparency and opacity. As the pigments get smaller and smaller, more light waves move through the particles and give it transparency, where the larger pigment particles give better opacity. And so, you know, in our mind, again, if we look at a red iron oxide, a particle that's about 1 micron in size maximizes, you know, our opacity of the pigment. So the key point that I want to talk about today is, and really the most misunderstood part of pigments, is the level of agglomeration or clustering. How easily does a particle cluster disperse? If you look at this particle and illustrated here, you see it's probably 15, 20 microns long, but it's made up of thousands of little pigment crystal particles. We think of dispersions in terms of grind, but these agglomerations also impact our color strength, the gloss, and the viscosity of, you know, the products that they go into. I'm not sure whether you can see this on your computer screen, but, you know, this is the same pigment, just with the one at the top, which has about a 10% strength advantage, has a higher surface area, therefore a lower level of clustering. And, you know, we call this higher color strength within certain limits. Higher surface area pigments need more liquid vehicles to wet them out. So while better dispersions result in higher strength and gloss, they may also increase your viscosity. And whether you're using a liquid color for coloring your plastics or in the melt itself, this level of surface area that needs to be wet out will impact your melt also. Finally, you know, larger pigment clusters will break through dry films, creating light scattering and reducing your gloss. And if you're producing fibers or film, you know, these large pigment clusters can block extrusions of thin fibers and cause pinhole breaks in plastic films. So, you know, even though the color's right, you're going to be able to, you might have some manufacturing problems by using a, you know, heavily agglomerated pigment particle. So how do we as pigment manufacturers measure these pigment clusters? You know, basically we're trying to simulate a process that our customers will use. We use what we call mesh retentions and Hegman gauges, and both of these methods are very dependent on how we prepare the sample. And we often get the question is, why don't we use modern particle size analysis to get an exact measurement? Well, most samples prepared for particle size distribution today with a technique like laser diffraction break up these pigment particles. So if we look at a laser diffraction of a red iron oxide on the left, we can see that it has an average particle size of about 1/3 of a micron, but we're not seeing anything above, 1.3 microns. Yet if we do a standard mesh analysis after dispersing the pigment on a high-speed disperser, while we're not seeing anything on the 44 micron mesh, as we go down to a 37 micron mesh, we start to see, particles showing up. And when we get down to a 20 micron mesh, we have 3/100ths of a percent of pigment particles that are greater than that. And that can affect, your processing. When you talk about coloring plastics, you can use both pigments and dyes. I am more of a pigment guy. So the things I'm talking about today impact pigments in plastics, but not necessarily dyes in plastics. The family of pigments that I'm most familiar with are iron oxide pigments, and these are the foundations of most color systems. When I'm asked to speak at technical seminars, there is sometimes I scratch my head because, I'm selling the same pigments that the cavemen used to paint on caves 30,000 years ago. These are iron oxides are the largest volume colored pigment used now and throughout history. These pigments are light fast, chemical resistant, UV absorbers, non-toxic, and provide a wide range of colors: reds, yellows, blacks, and browns. They can also be produced in both opaque and transparent formats. Because of their relatively low cost and durability, iron oxide pigments form the base colors to be shaded and brightened by most expensive organic pigments in color systems today. And again, I want to emphasize that second point there. There are not many pigments out there that are light, fast, chemical resistant, UV absorbers, non-toxic, and provide a wide range of colors. And they're relatively cheap compared to a lot of the brighter organics. So, they're a good foundation for developing your color systems. In its most simple form, iron oxide producers precipitate dissolved iron out of acidic solutions as an oxides. The color shade is dictated by the size and shape of the iron oxide crystal. For reds here, the larger that we grow the crystal, the more blue it gets, and the smaller, the more yellow shade or orange that we get the red iron oxide. We can plot on an A/B values of various red iron oxides to kind of show you the range. These are not just the red iron oxides that we manufacture at Cathay, but from across the industry of all producers. So, you can see we get some I think you can see my mouse, you get some very bright yellow reds and some really dark maroon wine color reds. We produce pigment particles, but you buy these pigment clusters. And the cost of a pigment is often dictated by how difficult these pigment clusters are to break apart. Pigment dispersions, when I use the term, is the process of wetting these clusters, applying enough energy to maximize their light reflectance, and then stabilizing the resulting suspension. The slide or picture on the left is a red iron oxide, the middle is a yellow iron oxide, and the right is a black iron oxide. So what creates these pigment clusters? First, we can have aggregates when pigment crystals grow together or are intertwined. Often these are caused by pushing the pigment yield per batch up too high. And they're the most difficult to disperse because you're actually having to break atomic bonds. Second, and most commonly, we talk about soluble salts. And these are residual salts from the acidic solution where we produce these iron oxide pigments. And these salts glue the individual pigment particles together. They also create a low pH value when they're dispersed in aqueous solutions. In black iron oxides, you have a certain amount of magnetic charges, and even the particle size and shape, especially when we start to get to longer needle-shaped acicular particles. These tend to bind together, just like a pile of nails or a pile of pins. And finally, even if we solve all the above problems, there's still an atomic charge of those electrons going around the nucleus of the atom that create a certain atomic charge called van der Waals forces. And this is enough energy to hold some of these small mass pigment particles together. Now, from a cost point of view, you want a low cost pigment, you might be getting a lot of aggregates and soluble salts. As you get higher, you reduce some of these forces that are creating these pigment clusters and making it easier to process. So in iron oxide, performance is often dictated by what's done with the pigment after the primary pigment particle is formed. We do washing steps, milling steps, and then a series of what I call post-processing. Iron oxide processing, what actually does it do for you? When we talk about washing, we're talking about moving this from a very acidic pH to a more neutral pH. When we talk about milling, we're talking about breaking up these pigment clusters to maximize the surface area, creating more surface to reflect the colored light that you're trying to achieve. And finally, I look at three main types of post-processing: blending, which minimizes color variation and targets a specific color shade; particle alignment, lowering the viscosity, especially in needle shape pigments like yellow iron oxide; and finally, surface treatments to increase heat stability when needed and to reduce reagglomeration or flocculation of pigment particles moving back together. What does all this mean to you as the pigment consumer? How do you select which pigment works best for you? Plus, the universal dilemma, cost versus quality. Selecting which pigment works best for you, everyone wants to make the best product based on their parameters, whether those are cost, profitability, performance, etc. But, in your business, are there corporate constraints? Is your project worth selecting a pigment that maximizes your performance? Or is there a generic pigment that you need to formulate around from a cost basis and a purchasing basis? It often comes down to, you can do the pigment processing yourself, or you can pay the pigment provider to do the work. I often like to say, to mill or not to mill, that's the question. You can buy pigments in powder, you can buy them from master batch people in plastic concentrates or liquid color, but it all is what works best for you. So what are your target specs? Is cost your prime driver, or are you trying to create a unique optical or physical characteristic? When I talk about a performance characteristic, for those of you who are old enough to remember the old bicycle brakes, You know, these were rubber pads that you squeezed on your tire and would slow your bicycle down. Now, you typically could get two types. You could get a black brake, which was pigmented with carbon black, or you could get a red brake, pigmented with red iron oxide. Now, the difference was in the performance. The black brakes grip better, making the rubber a little softer, but they wore out quicker. Whereas the red iron oxide brakes didn't quite give you the stopping ability that you got with the black, but they lasted forever. So, you know, in conclusion, you know, high quality pigments typically work in all applications, but are not always economically practical. Finally, how thick is your part? You know, has big impact on what you're doing, especially if you're producing fibers or film. So what does this washing step that I talk about, or neutralizing a pigment, do for you in the plastics industry? A low pH pigment can react with other fillers, especially calcium carbonate in your system, and create water and gas. These low pH pigments can dissolve in exterior applications, which will accelerate weathering. And finally, you know, low pH material can react with other additives, inhibiting performance. What does our milling step do for plastics? And really, milling is the most basic pigment manufacturing process. I find this picture on the left fascinating. We talk about cave paintings being 30,000 years old. This shell and mortar in the left picture are close to 100,000 years old. So mankind's predecessors were grinding pigments back then, which I just find fascinating. But what does the pigment milling do for you in plastics? First, it increases the color strength by increasing the surface area. The more particle clustering or agglomerate, lower surface area, lower color strength. You can use less of a stronger pigment to achieve the same color. And again, these larger pigment clusters can be bigger than certain films or fiber extruders and can result in lower gloss and a path for moisture and penetration, reducing weatherability. Iron oxide processing, post-processing, I talk about blending, particle alignment, and surface treatment. You know, the difference, I showed these reds before. The difference between these two reds is 1 micron. So often, to maintain a very tight color specification, you will need to blend your pigment batches together to minimize any variation, especially if you're talking about some type of natural iron oxide, because face it, the natural environment throws a lot more variables into that pigment, some that can be separated, some that can't. Blending solves all that. And finally, we can create, you know, like Mark showed with the complex inorganics, we can take, you know, certain base colors, blend them together to create a new color. Particle alignment is more for liquid color and for paints than, you know, your normal master batch plastic concentrate. But still, we do utilize some of these techniques when we need to, by reducing the void space between these pigment particles, making them easier to wet out in the resin, also allowing for higher pigment concentrations. And finally, surface treatment. You know, this is an area that the titanium dioxide people have been doing for years because they have enough volume to make a, you know, a special plastic grade TiO2. where colored iron oxide pigments tended to go into a broader range at smaller volumes. But, more recently, the iron oxide manufacturers began surface treating, first yellow iron oxides to improve their heat resistance. And we are also able to surface treat to improve processing steps. And we'll talk a little bit more about those when I get into iron oxides in general, which is now. Iron oxides are the base pigment, and I'm going to go through what pigments are acceptable for plastic processing. This is not a red iron oxide. This is a red iron oxide, and brightness is our biggest obstacle when it comes to coloring properties of iron oxides compared to, some of those brighter organics. But with that said, because of their durability, a lot of the iron oxides are used as a base color and then highlighted with brighter organics. Another problem that we have with iron oxides is only red iron oxide is actually heat stable enough for plastic processing as it is. You can see the yellow on your left is the yellow iron oxide. If I heat that above 150 degrees, it's going to turn red. If I take a raw umber, same thing, it's going to turn into a reddish brown. And if I take a black, it's also going to turn into a red color. So when we talk about yellow iron oxide chemistry, we take the hydrated iron oxide, add heat, and we result in a red iron oxide plus water. Just as a note, a lot of people are very confused when they look at the chemical analysis of a yellow iron oxide and says it's only 87% iron. But that's 87% iron when it's measured as Fe2O3, when you're taking out that water molecule from that. That's an aside. Typical iron oxide pigments for plastics applications are red iron oxide, heat stable, surface treated yellow iron oxides, tan zinc ferrites, black iron manganese ferrites, and certain heat stable brown iron oxides. And again, I'm going to run through these fairly quickly. I know it's getting late for those of you in Europe and in Asia. Red iron oxide is the most stable of the iron oxide pigments. They've got heat stability of greater than 300 degrees centigrade. We also do some surface treating to tailor processes for master batches and also make them ultra dispersible for films and fibers. Yellow iron oxide is where we start running into problems. Your normal yellow iron oxide, really, I don't like them much above 150 degrees C. If you're talking about a really, really low short dwell time, you can push that a little bit, and really they have limited application in high temperature fields. And what we do is we surface modify those and get that heat stability up to about 260. Now, there's two approaches to do this. This is the less expensive of the two. If you look at the ISO specs for color shift, they talk about 3 delta E. And so if you look at the surface treatment, we move from here with a traditional iron oxide of about 215 all the way up to 240 to 250. Most of my color work, people like colored variances less than 1 delta E. And you can see with this less expensive surface treatment, we're getting material that's somewhere between 220 and 230. If we look at a more durable coating, we can move that 3 delta E variance up to, 265, 270. Again, the 1 delta E probably for all of these more expensive surface treated products are, up here around 250. Before we started surface treating, we looked at making ferrites. These are very similar to what, Shepherd does, but on a larger scale. We're taking that yellow iron oxide, mixing it with the zinc oxide and firing it to replace some of the iron atoms with zinc atoms. These are heat stable above 300 degrees. They have a unique color index number, pigment yellow 119, because they're not quite the same shade as the yellow iron oxide. They're made by calcination in the 700 to 900 degree range. We micronize these to get those pigment clusters below 13 microns, so they're easy dispersible and heat stable. We can do the same thing with black iron oxides. Normal black iron oxides are only heat stable up to about 180 degrees. By replacing some of those iron atoms with manganese, we can push that up to above 300. Again, same thing. They're a calcination process, low Hegman, heat stable. And these are really an alternative black for where carbon black is not acceptable. In brown iron oxides, typical browns are mixtures of red, yellow, and black, and have limited heat resistance if you're using a yellow and a black iron oxide, about 180. We do make heat stable browns, either an iron manganese ferrite, a burn umber, or a red environ oxide. And again, these heat stable browns are above 300 degrees C, made by calcination. They're not quite as fine as the synthetic, so we micronize them down to about 20 microns, but easy dispersible still and heat stable. For those of you who aren't familiar with our range of environ oxides, these are kind of a takeoff of the natural iron oxides. We're taking acidic waste water from abandoned coal mines that's full of iron, dissolved iron. We channel these through a series of wetlands, and the acid is neutralized by the wetlands, which uses it as nutrients. When the iron can no longer stay in solution, it precipitates out as an oxide. And when these ponds are full enough, we're able to harvest them and process them like any other iron oxide. Mark touched a little bit about chrome. All of your major iron oxide producers also sell chrome oxide green. This is kind of a byproduct because the chrome oxide producers have bigger volume applications in refractories and other things, and just sell their crude to the iron oxide manufacturers who process that into the chromium oxide green pigments. Again, these are trivalent chrome compounds, non-toxic, applicable for indirect food contact in plastics, and compliant with various food contact applications. And again, one of the things we talk about, chromium 3 versus chromium 6. Chromium 6, I got the V and I wrong there, is toxic because of its solubility, but chrome 3 is non-soluble and therefore non-toxic. Again, one of the uses we see is astroturf. So those are basically my comments. I think I'm in my right time frame. I want to thank you for your attention. And do you have any questions?
The answer is yes. There is one question in the Q&A box. Can iron oxides be used in PVC processing without risks of heat stability or reaction with potentially HCl?
Well, that's kind of a difficult question because it depends on your stabilizing package. And this is just very, very general. In North America, we tend to use a stabilizing package in PVC that reacts with the iron oxides. I've been told that in Europe, they use a different stabilizing package, and iron oxides can be used in PVC. But it's a more complicated question than just what can the pigment do.
Okay, understood. I have, oh, okay, wait a minute. Questions are pouring in. Does the supplier control the crystal size and particle size as well for controlling tinting strength?
Well, the particle size and shape is controlled during the precipitation process, or where we get the iron oxide crystals. But if you remember, that color strength is actually coming from the level of agglomeration. So, you can have the same particle, same iron oxide pigment particle at different color strengths, depending on how those pigment clusters are broken down after the fact.
Thank you. Any more questions? I don't see anything. A big thank you. Oh, yes, another one pouring in. Yeah, positive feedback. So I'll join that positive feedback and I'll read it out loud. Great overview on conventional iron oxide. And a bonus question, any comment on trans oxides?
Well, trans oxides are actually, I touched base very, very quickly on transparent iron oxides when I talked about transparency and opacity. As we get smaller and smaller iron oxide crystals, some of the wavelengths that would typically have been reflected actually pass through the pigment particle and are reflected from the substrate, giving us transparencies. Now, the traditional problem with transparent iron oxides is that they are so small that they form very, very hard pigment clusters that are very difficult to disperse. We have a certain level of transparency with our new environ oxides that are making them acceptable as a replacement for the conventional precipitated transparent iron oxides now. But again, if you want that really, really bright trans red color, you're going to still need to use a synthetically produced transparent iron oxide.
Okay, thank you. I think we've had all questions. My response to you would be banana number 5, please. So I really enjoyed the way we see color and how it appeals to us. That was a great example. So thank you very much for the nice overview and the technical additions to both the visuals that we enjoyed. Have a good evening. Thank you all for joining. And for some closing words, I pass on to Tom, please. Bye-bye, everyone.